Thank you. Tomek powiedział, że moja prezentacja powinna być po polsku, dlatego nie będzie Fractal Architectures, będzie architektura fraktalowa. Ja jestem LWH, miło mi. Przepraszam bardzo, jeśli slajdy są przetłumaczone nieprawidłowo, bo nie miałem dużo czasu. For those who do not speak Polish, I was just saying that Tomek was joking a few days ago that my presentation really ought to be in Polish. And I was just apologizing for all of the mistakes. I am, in fact, joking. The rest of the presentation will not be in Polish. Anyway, that said, Fractal Architectures, I'm LVH. Hi. Or Laurens van Houtven, but that's kind of hard. Who am I? Well, that's my Twitter handle. That's my email address. I am supposed to be running Python and, well, all of the other official Python channels on Freenode, I guess. I recently accepted a job at Rackspace. So, yes, I live in Poland right now. Unfortunately, that will not be the case in the near future, but I will be coming back. I'm a Twisted Core developer. The reason I mention that is, well, here's a picture of Glyph, our fearless leader. It is a picture from many, many, many years ago. If I'm going to keep calling him our fearless leader, I should probably find a picture that is, slightly more intimidating. The reason I show you this picture is because I intend to continue a practice that was started by Glyph at last DjangoCon, the one in the US, I believe, where Twisted developers come to DjangoCon to talk about something that has absolutely nothing to do with Django whatsoever and is pretty much like antithetical to its very existence. So, therefore, Fractal Architectures. Glyph talked about the synchronous request response model and how everything really should be asynchronous, right? I'm going to talk about how you shouldn't have centralized data stores. Or, well, no, not how you shouldn't, but how I don't. And I think that's pretty antithetical to Django. So, let's talk about architectures. This is the DjangoCon in Warsaw, if I'm not mistaken. This is a pretty typical web app architecture, probably something that looks familiar to most people who use Django, I hope. So you have some load balancing. Load balancing talks to a bunch of application servers. The application servers talk to a bunch of outside services or inside services, a database, and probably some application level caching. So if you have like not too big an app, like, you have a load balancer in front, you have a couple of app servers, and they talk to two databases. Let's talk about scaling that up. First of all, your database. Unfortunately, you generally cannot scale most relational databases by just throwing more machines at it. You're probably going to need a bigger machine, and unfortunately for many of us, eventually that means that that machine is either going to come itself or from Oracle, or is going to run software from Oracle, which means that not only is it going to be bigger, it's also going to cost a lot more money. And how about scaling app servers? Well, scaling app servers, you can just more or less throw more machines at it if you want to handle more requests, but not really, because there's a lot of things that you can't really do at request time. There's a lot of things that eventually you're probably going to, add a queue, like, probably something based on Redis, or maybe, well, I guess Celery has a Redis backend. But, you're going to have a queue and a bunch of workers, and that's probably what you're going to need to do if you need more computational power. But if you look at this graph, and you squint just right, then there sort of is this unit of computational power or request handling in there. It's just like mushed over all of these layers, right? So what if we could have one of those things that actually has all of those things incorporated in it? So you have a hard application server layer on the outside, and then you have a slightly gooier database in the center, and then maybe some creamy caching in the center. Could you just have a bunch of those and magically handle more requests, and then put them on a bunch of servers and magically handle more requests? So this is not an idea that I came up with. I came up with it independently, but I'm not the first person to come up with it. The first people that I found calling it Fractal Architectures is a gaming company called Buga. They did it with Erlang. It's sort of similar to what I'm going to talk about in this talk, but it's also kind of different. The base idea is quite similar, though. So why do they call it fractal? Because if you look at it on a big scale, then you have something that handles requests, and when you zoom in, you still have something that handles requests, and when you zoom into more, then you still have something that handles requests. So up to some extent, you keep zooming in, and you see more or less the same pattern coming back. Perhaps a different, perhaps better name would be a sharded architecture, because instead of going from a database or a fixed number of databases per application, instead you go to a database per user or a fixed number of databases per user or per thing. It doesn't really have to be a user, it's just that's the sharding key that makes the most sense for 99% of applications. The point is that instead of going from k databases, you go to n times k databases. So the amount of things that you have is a function of your scale. Now, why would you possibly want to do that? Because, I mean, nobody actually likes sharding. Sharding is what you have to do when you go to be the size of Facebook, when you go to be the size of Facebook, and there is nothing else that will work. Everything else just, I mean, you can't have a single database because it'll fall over. It can't take that many requests, so you need to shard. Well, the first thing to remember is that there's a big difference between falling off a building and base jumping off a building. I mean, being prepared for something and intentionally doing it from the start is very different from trying to avoid something for a very long time, and then when you really have to, actually doing it. I hope to demonstrate that many of these restrictions actually result in strengths. For example, it has very interesting performance characteristics, and I already made the scaling up argument by construction, assuming that the thing that I'm talking about actually exists. Fortunately, it also scales down pretty well, which I hope to demonstrate. It has a bunch of economical and ecological advantages, because it turns out you often can do a lot more with significantly less iron. It maps well to a cloud because, well, it's the sort of thing where it's where it makes sense to add machines or remove machines on very, very small time frames. It also has certain monetary benefits. This is no longer a valid bill, by the way. In the early 90s, Poland had, well, hyperinflation, basically. So this is 2 million. This is a 2 million zloty bill, and, well, like I said, unfortunately, it's no longer valid. Someone told me that they remember buying a lollipop for 1,000 zloty. Even foreigners here probably think that that's a lot, but yeah. Anyway. I'm not suggesting that this is a silver bullet. Far from it. I mean, this is just something that I happen to have a bunch of fun with, and now I'm coming to troll DjangoCon with it. It might work good in some cases. It might also completely fail over. I don't know. I think it's the right tool for a bunch of things, but your mileage may vary. It's a good idea if most of the interactions that your users have can be described as something with their own data. As long as they're not all interacting with each other, and they're primarily working with their own stuff, then it tends to work quite well. For example, something that I think it would work really great for is if you have like a webmail app. Now, that might sound contradictory, because if you think about email, cicho, mam dać prezentację. Because when you think about email, that's the sort of thing where everyone interacts with everyone else, right? That's the point of email. You don't talk to yourself, you talk to the rest of the world. While that's true, those interactions can be just described by SMTP, but most of the interactions that some of you have with your email app are actually entirely with your own data. I mean, you're searching for stuff, you're tagging mail, you're looking up tags, you're doing whatever it is you're doing with your email, but you're fundamentally still only talking with your email, with your own email. In fact, if you were able to do most of that stuff that I just said with somebody else's email, that would be a bug. So, okay, I think this would be a good idea for a fractal architecture. Now the question is, where do we put this SMTP behavior? If you take the idea that I put to you earlier to the extreme, then you would have to say that, okay, well, all of these things are now going to grow some SMTP behavior. Of course, the other thing that you could do is do exactly what you would do now and treat SMTP as an external service, and your individual stores don't really care. So what should we do? Well, let's see what import this has to say about this. Well, first of all, special cases aren't special enough to break the rules. So that would appear to suggest that you put SMTP behavior in each and every one of your little stores. Of course, like most holy books, depending on who reads it and what result they want to get, there are completely conflicting things that you can get out of it. For example, although practicality beats purity, and in this case I would say that definitely SMTP is not a service that you should put in every single store or on separate servers, because it's probably, if you're trying to send email, it's probably a very bad idea to make your service indistinguishable from a spamming botnet. So yeah, try to use external services. Plus, if you're trying to be the next Sparrow, then your killer feature is probably going to be that your UI rocks, and it makes it possible for people to deal with significantly more email or in significantly more time. And then it's probably a good idea to just outsource your SMTP stuff. I promise that I'm not plugging these guys because they happen to be a Rackspace shop. This slide was in there way before I had anything to do with Rackspace. It's not even because they're nice people. It's not even because they use Twisted. It's not even because they gave me this nice t-shirt. It's because they just have a really kick-ass SMTP service. Another thing that I think it would be that would work really well for is Diablo 3. Now, I took most of these slides out. It was more current back when Diablo 3 was released but didn't actually work. Now they've fixed most of their scaling problems because nobody seems to actually play their game anymore, which I guess fixes a lot of the problems they had. That said, I'm going to talk about some of the tools that I used to build this. First of all, persistence, for which I use SQLite, which I guess the choice for that is pretty obvious. It's a bunch of small stores. SQLite is absolutely perfect for that. It has a couple of other advantages. Having developer and production parity. Okay, fine. If you use Postgres, you can do that because I don't know, you have like Vagrant or whatever, and it sets up a Postgres box exactly the same way that the Postgres box is set up in production, right? Because that never goes wrong. Whereas SQLite, I mean, it's in the Python standard library, for Christ's sakes. There are very, very few ways that SQLite differs, especially if if you have like an OS X laptop and Linux servers. There's very, very, very few differences. I don't actually use SQLite directly. I use Axiom, which is a small object store on top of SQLite. Who here has heard of Axiom? And of those people who heard of Axiom, who heard it through me or didn't hear it? Yeah, okay. So, oops. Okay, for those of you who've seen this before, I'm sorry, but why do I like Axiom? It's simple. It doesn't really try to hide the fact that it's relational. There's a direct mapping from tables to objects. If you want a many-to-many relation, then, well, you're going to have a join object. It works on SQLite, and it only works on SQLite, which has, that sounds like a limitation, but in this case, I don't care because I want SQLite anyway. And because they only have to work for one particular database engine, that gives them a number of optimization opportunities. You can use it entirely in memory, so that makes it a lot easier to just like do random experimentation, just throw open a REPL, and boom, you have an Axiom store. At the same time, it's really sophisticated. For example, for schema migrations. I mean, it has a full schema migration system where, you can add things, you can remove attributes, you can even create new objects in your migration. You could destroy the old object when upgrading it and create multiple new objects. So basically, pretty much anything you can think of that you could possibly want to do in a migration, Axiom will let you do. Part of the reason, of course, that it can do this is because, well, you're dealing with small local SQLite stores, which makes a lot of things a lot easier than if you have to deal with some giant Postgres database somewhere. Don't get me wrong, I love Postgres, but it is very strongly typed. You can't just put random bytes, and it doesn't support Python 3, but at least you know that if you use Axiom everywhere, then at least Unicode-wise, your app probably isn't broken. It has a scheduler, which allows you to persist scheduled event. That's one of the reasons that I end up not needing a workers in a queue, because you just persist that the thing that you're going to do at some point in the future, and you let app servers handle it, and as long as they don't block the entire thing, then that's fine. It has file storage, which is nice, and it has a thing called power-ups that I couldn't possibly hope to explain in this talk, but let's just say that you pretty much can put arbitrary behavior in a SQLite database, which is really, really, really cool. It also behaves as a sort of dependency injection system, which makes testing fantastically cool. Anyway, I don't know why more people don't use Axiom. It's great. But I guess one of the reasons might be that the documentation is, well, it was really, really terrible, and it didn't help when that one single machine that it was hosted on totally crashed and took everything with it, and now you have to go get your documentation from like archive.com. That said, I am trying to write I've written like most of the basics of sort of a book, kind of like the Django book, I guess. Except, no, not like a Django book, because people don't like the Django book anymore. But I've been trying to write some documentation for Axiom. If you're interested at all, go take a look. If you like the first few basics of the documentation, please let me know. I would like to write more advanced stuff, but I'm not going to do it if nobody cares. Another reason why I like that is the scaling down argument. I mean, there are very few things that scale down better than a local SQLite store. I mean, that's pretty much the lowest common denominator for how easy it can be to scale something down. Like, import SQLite 3. That's pretty much all you have to do if you want to get a SQLite store. Now, that said, there are alternatives, of course, that you could use. I mean, you could use technically Redis. You could probably even use Postgres. That wouldn't be too much of a problem. Just have on each server, you have a Postgres machine running. Just give each running instance, like, I don't know, their own database or something. One thing that I don't think you could use is MySQL, because you should not use MySQL ever for anything. So that covers short-term persistence. That's where things are as you're working with them. You also need longer-term storage. Why? Well, one reason is monies, because all of your local storage on your local server might be fast, but it's also kind of expensive. And very often, I mean, when you're not working with the data, it doesn't really make sense to have it in very, very fast local storage. It makes more sense to put it in something perhaps further away, perhaps with higher latency, but cheaper. The other reason is durability, because, I mean, you can use services like, I don't know, well, I'm going to give a few examples, but things such as S3 or OpenStack Swift, where you get durability for free, basically. They have very, very high data durability, whereas, obviously, local disks do fail. They can and they will fail when the most important customer's data is on them. So. And the other reason is that if you have a server and it gets overloaded, then long-term storage can be sort of an in-between, go-between for temporarily storing the thing when it goes from one server to the other. So basically, if servers become overloaded, then you don't want that store to be on that particular server because, well, that's where all of the API requests are going to go. So obviously, you don't want more API requests. So options, like I said, OpenStack Swift or Amazon S3. The biggest problem with these is that, is my understanding that neither of these currently support differentials. The problem is when you end up doing this, okay, fine, you have some small store. Usually it's not much of a problem because all of the user's data put together is like, what, maybe a megabyte or so? The problem is that only every time a user does something, like maybe only a couple of kilobytes change. Or, okay, fine, and if they upload a couple of pictures, maybe there's like an extra megabyte or something. My point is that the vast majority of a user's data doesn't really change, or at least when I was with the application that I was working on. So it would be nice if we had something that like allowed you to push differentials out, because then obviously your updates would be a lot faster. There is something that does that. It's called Dropbox. But I didn't really want to tell anyone that like my production application uses Dropbox as a persistence backend because, yeah. Like I said earlier, I use Twisted for this. What you use isn't really that important. There's two reasons I want to mention that. First of all, manhole. So if you have no idea what manhole is, it is, imagine being able to SSH into any working server and just get a Python REPL and just get the objects that the server is actually working with right now and be able to modify them and instantly see behavior changes. So manhole just does that. And when everything is on a particular server, so the entire store, all of the user's data, that feature just becomes all the much more powerful because, hey, if a user is experiencing a bug right now, you can actually SSH into that machine and see what's going on in the store, not just what's going on in the user's screen. Now, like I said, anything will work. The only reason I mention this is because, well, Twisted uses an event loop. It's single-threaded. It's concurrent, but it's not parallel. And it turns out that Axiom blocks. The Axiom API is completely synchronous. It does not try to play nice with the event loop or anything. But it turns out that this is not a problem. Why? Because local SQLite is really, 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 really fast, especially when your stores are so small that they pretty much just fit in memory. So yeah, turns out local SQLite, good. Which brings us straight to performance. I would give you some benchmarks, but the problem with most benchmarks is, well, they're not very good. There's a bull on this slide. I have no idea why. One of the reasons that it's kind of hard to give benchmarks is because the entire system is so inherently completely different that it would be more or less impossible to give you a useful benchmark that would actually tell you anything, so instead I'm not going to give you any benchmarks. However, I am going to try and reason with you a little bit. It would seem that there are two obvious ways to getting better performance. Either you do less work or you do it faster. This is a latency graph. So the scale is logarithmic. It's in seconds, I believe. No, it's in nanoseconds. And it goes from L1 cache hit all the way on the left, which is, as you can see, so fast that it doesn't even show up on the logarithmic scale. Then an L2 cache hit, a RAM, having to go to RAM to get something, SSD latency, LAN latency when you're in a data center, then the seek time for spinning Rust, and finally getting a packet from Fremont in California to Amzix in Amsterdam, the Netherlands, and back again. Now, other than what this should obviously tell you is that yes, SSDs are really good. I'm guessing nobody knew that, right? And secondly, local means really, really low latency, because a lot of those things, especially if you manage to hit RAM, you're talking significantly lower latency than, for example, having to hit anything on the network. And then we're not even talking about query latency. And most of the time, query latencies are, well, I would hope at least for most, or at least the vast majority of queries that you do, that your query latency is significantly lower than your access latency. It gets even better because it's not even big remote store versus big local store. It's big remote store versus very, very, very large number of small local stores, which means that even if you have to do, let's say, a complete table scan, like, let's just say, obviously SQLite does support indexes, but let's just say that you don't index anything, right? And you have some tight loop that basically does a complete table scan every single time, right? Except, hey, it's only like 50 rows or something, so it doesn't even really matter. Generalizations are always wrong, but in a lot of cases, computation isn't really the bottleneck, and if it is, you can move it somewhere else so it stops being the bottleneck, so it's not really a very hard bottleneck. Getting data in the right place at the right time is. This is just another instance of data locality, except when most people talk about it, they're talking about, I don't know, like CPU caches or something, like some algorithm that is cache oblivious or cache aware. This is basically exactly the same idea, but just applied at a much higher scale. That said, I did write this benchmark. If someone really, really wants to know how quickly Axiom can insert items into a store or something, I wrote a thing called Axiom Bench. And it has tests, it has full coverage, and it works, and it shows you how fast some things are. So if you do care, just get that. So, again, how long was my slot? 6 minutes? Okay. So I'm going to play advocate of the devil a little bit with my own thing and try to poke holes in it. A problem that some people, once they've thought about this for a little bit, have is that they say that some of my data doesn't fit in. Because you have all of these wonderful user stores, and then you have some stuff around it that doesn't really fit. For example, let's say that you're doing aggregate data, or you're doing statistical analysis, or you're doing some machine learning, or even like really simple aggregate. The problem with this is that it's users.aggregate, clearly, and not user.aggregate, so where do you put it? Another problem is encyclopedic data. Let's say that you have to look something up. Stuff that I've been doing involved a lot of zip codes. And clearly, zip codes don't belong to any given user, but for any given user, I do need to be able to look up zip codes and, or go from location to zip code or the other way around. So that's world.data and not user.data. Once again, where does it fit? So this is kind of a square peg round hole problem, and there's pretty much 3 ways of dealing with it: duplication, delegation, and separation. If you duplicate, well, duplicate does what it says on the tin. You just basically copy everything into every store. Everything's local. It's pretty simple. You don't have to worry about where everything is. But of course, duplication. And one of the problems is size. What if this is too much data? If you want to, I don't know, if you want to have like topography maps of the entire Earth, then that's kind of a problem if you need to copy those for each user. And also, if some of that information changes, like for example, zip code data, most people think it never changes, but it actually does. And sometimes you really do run into problems because you have stale data. So I guess that's a good idea if you have limited data and limited mutation. Something that someone else has tried is delegation. Personally, not a big fan. The idea is that you basically pick some store that it sort of, kind of belongs to, and then you put it there. The problem is, of course, that it's the good thing is that you don't have to duplicate anything, but it's awfully complex because you have to figure out where some data belongs, and hopefully that's a useful measure. But maybe you just have you just made something up and you just like take a hash and do mod something and then figure out which store it goes into. I guess sometimes it's local. It might make sense if your usage is highly correlated with a particular user. Like, I don't know, if you have sales data that's sharded by area or something, then most of your queries will be local, and at least your aggregate queries will cross shards predictably. The biggest problem with it is that it's very tightly coupled because, well, obviously, changing it is more or less impossible. It takes a lot of effort. My personal favorite is separation, where you basically go, okay, fine, those things don't fit, therefore let's just make them stores. You can just have another store. I mean, I never said that just because, well, we have one store per user, that doesn't mean that all of your stores have to belong to a particular user. You can just have a bunch of data that has nothing to do with users. And you have this one group of stuff that's user data and this group that's not user data, but there's nothing wrong with that. Probably the most important problem is that querying over all data is hard, by which people mean that querying across stores is hard. Yes. Yes, it is. There's 2 reasons people tend to care about this. It's either data analytics or transactions across stores. For data analytics, most data sets just use separation. Seriously, I've used this and it works fine. I mean, most of the time I use scikit-learn if I want to do some kind of machine learning stuff. And just put all of the results of that in a separate store. It works fine. For big data, I guess there are specialized tools. I mean, if you have Hadoop, then you probably want like HBase or Hive or something. People have suggested to me that there might be a missing sweet spot where, if you had a traditional Postgres centralized database, then it would carry you a little bit further than all of these little tiny SQLite databases. Maybe, but my main argument against that is that most people don't really have big data, and just because you're using Hadoop doesn't mean you have big data. I mean, and if you do have big data, then you don't really care about my opinions on it, and you probably don't really care about this architecture either, so The other reason is transactions. Now, cross-database transactions do exist. Some people were talking about it earlier. SQLite does have attached database, and there's DB-link. You could do it in Python if you want distributed transactions, because then we can all implement Paxos and everything will be right again with the world. Of course, the problem with Paxos is that if you look at it too long, your brain starts to hurt. And well, I implemented Paxos twice, and that was 2 times too many. And when I say I implemented Paxos twice, what I mean is I think I implemented Paxos, but I honestly don't know. Fortunately, this has actually recently been fixed somewhat because Raft. So if you are at all interested in distributed computing, recently there was a paper that came out called Raft. It won big points with me because the first 2 pages were basically about Paxos is great, but it's way too complicated and nobody actually really uses Paxos, or they don't really know if they use Paxos. So Raft is an algorithm that does exactly the same thing. It's a consensus algorithm. It's a distributed consensus algorithm, except it's intended to be understandable by humans. And I read the paper once, and I think I more or less understand what it does, which is great because I think I read the Paxos paper, well, multiple Paxos papers like 15 times, and I still don't have a clue what any of the 4 phases do. The last problem is that there are no existing tools or frameworks. Now, I hope that I demonstrated in this talk that the tools sort of kind of exist. You just have to bend them in ways that they aren't usually bent for them to do something like this. But it is definitely true that you don't have a wonderful framework that will magically do everything for you. And you don't have magical services that will magically host this. Because, for example, this is really hard to host on Heroku. Heroku tells you that you have basically no local storage that is at all persistent, and this relies on having local storage that's persistent. And a lot of the tools you're going to have to make yourself. Now, a very smart man once said, "Be the change you want to see in the world." And many years ago, some people, many of whom Twisted developers still, wrote a thing called DivMod Mantissa. I'm writing a thing called Exponent, which is basically this. I use semantic versioning. The version number is 0 point something, and that first number is a 0, and I mean it. Last week, I killed the entire authentication package, and I will do it again. I will break your API. Please do not use this in production. I warned you. Here be dragons. Anyway, I think that's the end of my slides, and thank you for listening to me rant about something that has nothing to do with Django. You all have been extremely patient.